Hello, this is the fourth lecture of the cognitive modeling course focused on connectionist models of human cognition. I told you in the previous lecture that the traditional symbolic models were followed by a new wave or a new generation of models called connectionist models. These models were originally inspired by human brain. What you see on the left is a hand drawing of nervous cells by Ramon A. Cajal, who was one of the pioneers of the modern neuroscience. And you see how neural cells are connected to each other and supposedly pass information to one another. Let's zoom in on what the architecture of a single neural cell looks like in human brain. Of course, there are different types of cells, but this is one example here. So you see that the cell has a core or a nucleus where the information is being processed, and it also has a bunch of input channels, which are called dendrites, and this is where the input signals are received by the nucleus. After some processing is done on these input signals, the cell generates an output signal on this branch here, which is called an axon. So basically, the cell is a very small information processing unit which receives a bunch of input and then generates one output based on some processing that takes place inside the cell. This idea seemed simple enough to simulate in the form of a model. So you can think of an artificial neural cell which has a processing core, and it receives a bunch of input and it generates a number of outputs. And on each of these channels where the input is received or the output is emitted, we can also impose some weights. So some of these input channels might have a higher influence on what output the model generates. So these W's that you see, these are basically different weight factors for each input or output channel. So already you can see that the way knowledge is represented in a model of this kind is different from a symbolic model. We are basically looking at certain activation patterns over many neurons and the strength of connections between them. So as I said, these neurons are actually connected to each other, and this is a more high-level scheme of a sample connectionist model. So you have several neurons which are represented in the form of these colored circles, and they're connected to each other, meaning they receive information from each other or they pass some information to the other neurons. The red neurons on the very left side are called the input neurons or input units. These are the ones that receive the information or the signal directly from the outside world, from the outside of this model. So whatever the function of this model is, there are certain input signals that the model receives, and this is done by the input units. Similarly, on the right-hand side, you see another set of red neurons, which are basically the output units. These are the ones that generate the kind of information or signal that's then passed to the outside world. In other words, this is what the behavior or the response of the model is to a certain stimuli. In between, you can have one or more layers of neurons called the hidden layers, which basically connect the input and output units together. Hidden layers play a very important role. The more layers you have, the higher the computational capacity of your model will be. These are called hidden because they don't have any direct contact with elements outside of this model. But they are actually playing a very important computation role here. So what do these signals exactly look like? What kind of input we are talking about, and how can this input be distributed? So you see that instead of a single symbol which has a single value, now we are dealing with a bunch of features or a bunch of signals that are received simultaneously by a number of input units. So depending on the task that the model is developed for, these features or these signals have a completely different nature. For example, if we are talking about a categorization model, we can talk about signals such as shape or color, or whether the item we want to categorize is edible or animate, or any other feature that your model thinks is important in categorizing. So to give you an example, if we have an apple as an input, then the shape feature has the value round, and the color feature has the value red, and so on and so forth. And similarly, for another object such as cat, we have different values for shape and color and edible and animate and the rest of the features. If you want to translate these values to a language that computers understand, you will end up with a bunch of numerical values on these features. So now we are getting closer to what an input signal actually looks like. So this is how the input to a connectionist model is represented, as a vector or a sequence of numerical values. Similarly, if we want to build a model for building the past tense form of an English verb, we have to somehow represent the input to this model as a set of features. What would these be? For example, depending on the model of phonology, it could be a set of phonemes that form the root of the verb, or it could be a set of syllables, or if you're actually modeling the written form, this could be a set of characters or letters that form the root of the verb. For example, for the word walk, you can see the phonemes that the model receives as input. Similarly for the word bring. And then the output would again be a set of phonemes. Sorry, this is for the previous model. So output also has a distributed character, right? It also could be a set of values instead of a single value. So for the categorization model, we are talking about which categories an input item belongs to. These categories could be things like animal, food, toy, furniture, and so on and so forth. If you're talking about the cat as input, then the output should be yes to the animal category and no to all the other categories. Or again, in a language that's more suitable for computers to process, this should be a value 1 for the animal category and 0 for all the other categories. In the case of the English past tense model, our output should be the form of the English past tense of the verb. This again could be a set of phonemes or a set of syllables or letters. For example, if our input was the verb go, our output should be a representation of the form went as a set of phonemes. So you see that we now have to think a little bit differently about how to simulate the input to the model and how to generate the output for each task that we want to simulate using a connectionist model. Now, what I have talked about so far has been only about the static representation of knowledge. But how does the model actually learn to produce the correct set of features based on receiving a set of features as input? As I said before, the core of each unit is a simple processor. For example, it could be that it just sums up the input values weighted by the weight of each connection, and then depending on this sum of the values, it generates an output value. But then the model has to learn to adjust its behavior over time based on the past experience. This is what humans do, right? They adjust their behavior based on their past experience. So in a well-known category of connectionist models, this happens based on the feedback that the model receives from the environment. For example, let's say the model receives a set of values as input. It generates an output by passing these values through several layers. And then once the output is generated, the model receives some feedback about what the correct or the target output should have been like. So the model then can measure how much of a mistake it made, and it can adjust these weights on the connections to make its prediction closer to what it should have been. So the model basically reconsiders its internal architecture by adjusting these weights W to then generate the correct or desirable output for a given set of input. If the model does that over and over again for every single input that it receives, by first generating the output based on what it has learned so far and then receiving feedback and adjusting the internal weights, then over time it actually learns not only to produce the correct behavior but also generalize this behavior to cases that it hasn't seen before. So in that sense, a cognitive process in a connectionist model is simulated as a large number of neurons that perform basic computations in parallel. So each of these circles that you see is performing a computation by looking at all the inputs that it receives and all the weights of the connections on which these input signals are received, and then calculates and generates an output value. So connectionist models have certain advantages. They, first of all, learn abstract knowledge from exposure to very specific instances. So they learn from experience by observing what input leads to what kind of output, but they are actually able to generalize these instances to a more abstract level. They are also easy to adapt to new domains and learning tasks. So in a sense, they are very flexible in terms of their learning mechanism and the represented knowledge, similar to what human brain actually shows. But there are also certain disadvantages that come with them. First of all, the way the model learns is very implicit. You can't really examine the knowledge that the model learns for a particular domain by looking at these numbers and these weights and then interpreting them very easily. So they are more or less a black box where things happen, but these things that happen are not easily understandable by humans. Also, the second one is the main limitation, or was the main limitation. They are very computationally heavy, and they are not very easy to scale up to realistic problems. So when connectionist models came to the scene, if you wanted to, for example, simulate some aspect of learning and using language, then you could not go beyond a very small vocabulary or very simple constructions for your sentences. If you wanted to talk about a model of human memory, you could not handle more than a few tens of items at a given time, because these models were very slow to train and they're very, very computationally heavy. This actually led to the demise of these models. They became less and less popular because they just could not scale up to the level where people were interested in the natural scale of things. However, this has changed because over the past decade, the computational power has really scaled up, and also the new technologies in parallel computing have allowed the researchers to resurrect these models and use them in a much larger scale for modeling various aspects of cognition. What has really changed the nature of these models is the ability of the researchers to use many, many more hidden layers. So now you have models with several hidden layers where the distance between the input units and the output units has vastly increased. This is what people talk about when they talk about deep learning, which you might have heard in the media, by making these models very deep by adding more and more layers. The example that I am showing you here is an example of a model of object categorization from images, which was proposed and released by Google a few years ago, and it received a lot of coverage because this model actually showed very interesting characteristics that emerged as a result of what the model saw in the data. For example, each layer seemed to be able to extract more and more abstract features from an image. The lower layers were focused on low-level features such as edges and shadows and then diagonal lines, and then gradually you could find specific nodes that seem to be specialized in detecting human faces, for example, or cats. And so it seemed like even though none of this was explicit, it seemed that the model is able to reorganize itself so that it actually detects the most dominant and common patterns in the data, in this case, the images. Okay, I'm gonna stop here, and in the next lecture we are gonna talk about probabilistic models, which are a more general family of models which look at the statistical characteristics of